So far, we have only been talking about one type of current, and that is a direct current. In this video, we're going to explore another type, that is an alternating current. And it turns out that an alternating current is more of what we use in our everyday society. And the reason why we will explain later on after we learn about electromagnetic induction in chapter 21. So, with a direct current, you have the relationship that voltage is equal to current times resistance, Ohm's law. You have a steady voltage, so you have a steady current. And so no variation in your current at all. However, if we were to build a circuit where instead of having a regular voltage, you replace that voltage with an oscillator so that at one point in time it has a positive voltage, and the next point in time it has a negative voltage, the currents will be fluctuating back and forth as well. And so it ends up becoming a sinusoidal pattern. And so we can depict the currents and also the voltages using sine functions. And this is what the function would actually look like. The voltage of an alternating current would equal some peak voltage times the sine of omega t, where omega is equal to 2 pi divided by the period, or 2 pi times the frequency, depending on whether you're given the period or the frequency. It's the same thing. So that's the voltage, but remember that current is just voltage times resistance. So our current is that also follows the exact same pattern. Your current at any point in time is going to equal some peak current times the sine of omega t. So we can carry this on a little further and start talking about electric power in an alternating current. We could do this by saying power is equal to current times voltage, or power equals voltage squared divided by resistance. Here we're looking at power equals current squared times resistance. They will all give us exactly the same result. And that is your current is going to be your peak current times the sine of omega t. But since current is squared, then you end up with a sine squared term in here. And so sine squared only oscillates between 0 and 1 instead of going from -1 to +1. As such, the electric power of an alternating current is only going to be oscillating between 0 and its amplitude, which is the peak current squared times the resistance. Now, if we want to find the average power, then we need to find the average current. The average current squared. Since the current squared oscillates between 0 and the peak current squared, the average then would be right in the middle. It would be 1/2. And so the average power of an alternating current would be 1/2 of the peak current squared times the resistance. Like I said, we could do this following power equals current times voltage, or we could do power equals voltage squared divided by resistance. You end up with the same result. And we can put up this form as well if we'd like. So 3 different ways to find the average power of an alternating current. Why would we want the average power instead of the peak power like we have in this slide? Well, the peak power kind of gives misinformation, because you're saying you're getting 20 watts of power when really, on average, you're only getting half of that, 10 watts. And so the average power is a much better tool to describe the power rating of an alternating current, instead of giving false information thinking that there's more energy actually being given in a given amount of time. So that's how you find the average power. Can we find the average current or the average voltage? Well, here we have a problem. Remember that current and voltage both oscillate between the positive and negative peaks. So voltage between positive and negative peak voltage, and your current between the positive and negative peak current. In other words, it's a sine function. Well, what's the average of a sine function? The average of a sine function is 0. And so really, your average voltage and your average current are equal to 0. Well, this gives a problem. So what we need to do is first of all get rid of the sine, then take the average, and then fix whatever we did. So we're going to take our peak voltage, excuse me, not our peak voltage, our voltage at any point in time, and then we're going to square it. And we can do the same thing with our current. Now that we've squared it, we've gotten rid of any negative values, so now we can take an average of the two variables. Now we have our average, but it's an average of the voltage squared, or the current squared. So we have to get rid of the square by taking a square root. Now, this may look familiar back from chapter 13. We took the root of the mean of the square values. Yes, we're talking about RMS voltage and RMS currents. Now, fortunately, this is pretty easy to calculate. We'll just do it with the current. The voltage is exactly the same. So if I is equal to I naught sine omega t, then I squared would be I naught squared times sine squared of omega t. And then the mean value, so mean of I squared would equal, well, I naught is just a constant, so its average is itself, times the average of your sine squared omega t's. Well, remember, we already did the sine squared omega t back here. And specifically, we found that sine squared of omega t is going to equal 1/2. And that's where the 1/2 came from in that equation. So the average I squared is going to be 1/2 of the peak current squared. Okay, so that's the mean of the squares. To get RMS, or root mean square, we have to take the square root. And that is going to equal 1 over the square root of 2 times the peak current I naught. And that's what we have right here. And square root of 2 is a lot easier. 1 over the square root of 2, we calculate that as 0.707. Derivation of the RMS voltage is exactly the same, no difference at all. And you can see this is a lot easier to calculate than the RMS velocities we did back in chapter 13. So RMS current is simply the peak current divided by the square root of 2, and the RMS voltage is the peak voltage divided by the square root of 2. Now, let's consider this here quickly. Let's look at United States typical voltage. If you plug something into an electrical outlet, really, well, we say that we have a voltage of 120 volts. A standard household outlet is a voltage of 120 volts. Well, what are we talking about? Are we talking about peak current? Are we talking about peak voltage, RMS voltage, or voltage at some point in time? Well, turns out that this is the RMS voltage. But remember that the RMS voltage is the peak voltage divided by the square root of 2. So what is the peak voltage in our standard United States household electrical outlets? Well, that's going to be the square root of 2 times 120 volts. Gives us a peak current of, let me go ahead and calculate this, square root of 2 times 120 gives us 169.71 volts. About 170 volts is the peak voltage in our electrical outlet. But we're not giving 170 volts all the time, so it doesn't make sense to say that our outlets are 170 volts when on average really our voltage is only somewhere around 120 volts. That's why we often use this number, which is the RMS voltage. And again, similar story for electrical currents and in an alternating current.